From time to time, humanity extends its habitat and explores new places. In the past, we were looking for new places on Earth, and now we're looking for outer space. As the exploration thing changes, the transportation changes too. So, if we started with horses, wooden ships, cars, and so on, now we're in the era of rockets. Soon, maybe each individual could have their rocket. But until that, it's important to know how they work, or even how the rockets are made. That's it. Today's video topic is rockets and how they are made. Firstly, start with how rockets work, how they lift off, take flight, and leave Earth. The first person to seriously study the rocket's potential for space travel is Russian schoolteacher and amateur scientist Konstantin Tsiolkovsky. First published his conclusions in 1903. He correctly identified the launch as one of the biggest challenges, the moment where the rocket has to carry all the fuel and oxidant it needs to reach space. As its weight is at maximum and a huge amount of thrust is needed just to get it moving. As the rocket gets underway, it sheds mass through its exhaust, so its weight is reduced and the same amount of thrust will have a great effect in terms of accelerating the rest of the rocket. Tsiolkovsky devised a complex equation that revealed the necessary thrust force needed for a given rocket maneuver, and the specific impulse, how much thrust is generated per unit of fuel needed for a rocket to reach space. Although he did not live to see his work recognized, Tsiolkovsky's principles still underpin modern rocketry. Rockets must delicately balance and control powerful force to make it through the Earth's atmosphere into space. Isaac Newton's third law of motion states that every action has an equal and opposite reaction. So the action force that drives the exhaust out of the rocket nozzle must be balanced by an equal and opposite force pushing the rocket forward. Specifically, this force acts as an upper wall on the combustion chamber. But because the rocket motor is integral to each rocket stage, we can think of it acting on a rocket as a whole. As the rocket gains speed, keeping the direction of motion closely aligned with the direction of thrust is critical. Gradual adjustments are needed to steer the rocket towards an orbital trajectory, but a severe misalignment can send the rocket whirling out of control. Most rockets, including the Falcon and Titan series, and the Saturn V moon rocket, steer using gimbaled engines mounted so that the entire rocket motor can pivot and vary direction of its thrust from moment to moment. Rockets are the key to exploring our solar system. But how do they go from orbit to deep space? The first stage of any spaceflight involves launch from Earth's surface into a relatively low orbit, around 200 kilometers up above the vast majority of the atmosphere. Here gravity is almost as strong as it's on the surface, but a friction from Earth's upper atmosphere is very low. So if the upper atmosphere stage of the rocket is moving fast enough, it can maintain stable, circular or elliptical trajectory, where the pull of gravity and the vehicle's natural tendency to fly off in a straight line cancel each other out. Spaceflight engineers and mission planners often refer to the delta V required to accomplish a spaceflight maneuver, such as a change in orbit. Strictly speaking, the term delta V means a change in velocity, but engineers use it specifically as a measure of amount of impulse or thrust force over time. Sending a spacecraft from one planet to another with minimum delta V requirements involves injecting it into an elliptical orbit around the Sun, called the Hoffman transfer orbit. The spacecraft travels along a segment of the elliptical path that reassembles a spiral track between the orbit of the two planets and requires no further thrust along its journey. On arrival as its target object, it may use gravity alone to enter its final orbit, or it may require a burst of rocket thrust in the opposite direction, usually accomplished by simply turning the spacecraft around in space and firing the motor before it can achieve a stable orbit. If you like this video by far, don't forget to like it. For more videos like this, please subscribe to the channel. The study of rockets is an excellent way for students to learn the basics of forces and the response of an object to external forces. In flight, a rocket is subject of the force of weight, thrust, and aerodynamics. Many parts make up a rocket. For design and analysis, engineers group parts that have the same function into system. There are 4 major systems in a full-scale rocket: the structural system, the payload system, the guidance system, and the propulsion system. The structural system, or frame, is similar to the fuselage of an airplane. The frame is made from very strong but lightweight materials, like titanium or aluminium, and usually employs long stringers which run from the top to the bottom, which are connected to hubs, which run around the circumference. The skin is then attached to the stringers and hoops to form the basic shape of the rocket. The skin may be coated with thermal protection system to keep up the heat of air friction during the flight and to keep it in cold temperatures needed for certain fuels and oxidizers. Fins are attached to some rockets at the bottom of the frame to provide stability during the flight. The payload system of a rocket depends on the rocket's mission. The earliest payload on rockets were fireworks for celebrating holidays. The payload of the German V-2, shown in the figure, were several thousand pounds of explosive. Following World War II, many countries developed guided ballistic missiles armed with nuclear warheads for payloads. The same rockets were modified to launch satellites with a wide range of missions: communications, weather monitoring, spying, planetary exploration, and observation, like the Hubble telescope and JAMESWEBB telescope. You can see the videos about JAMESWEBB telescope on our channel. Special rockets were developed to launch people into Earth's orbit and onto the surface of the Moon. The guidance system of a rocket may include very sophisticated sensors, onboard computers, radars, and communication equipment to maneuver the rocket in flight. Many different methods have been developed to control rockets in flight. The V-2 guidance system included small vanes in the exhaust of the nozzle to deflect the thrust from the engine. Modern rockets typically rotate the nozzle to maneuver the rocket. The guidance system must also provide some level of stability so that the rocket does not tumble in flight. Most of full-scale rockets is a propulsion system. There are 2 main classes of propulsion systems: liquid rocket engines and solid rocket engines. The V-2 uses liquid rocket engine, consisting of fuel and oxidizer tanks, pumps, a combustion chamber with nozzle, and the associated plumbing. The Space Shuttle Delta II and Titan III all use solid rocket strap-ons. The various rocket parts described above have been grouped by function into structure, payload, guidance, and propulsion system. There are other possible groupings. For the purpose of weight determination and flight performance, engineers often group the payload, structure, propulsion structure, and guidance into a single empty weight parameter. The remaining propellant weight then becomes the only factor that changes with the time when determining rocket performance. That's all about rockets. Now we know a little more about how they work and how they are made. Maybe we can fly with them soon. If you like the video, hit that like button and don't forget to subscribe to the channel.